welcome to the Signal Path. In this episode, I've got another product review for you guys. Now, I've been wanting to get myself a CNC machine for a very long time. Of course, in my lab, I'm mostly interested in making PCBs, and a CNC machine can be used for that and a whole bunch of other applications. I was surprised to find out how many different models are actually available across a huge range of prices. So eventually, after doing a lot of research, I ended up buying the Carbide 3D's Nomad 883 Pro, which you're looking at. Now, this is not a cheap machine. This is about $2,500. And any accessory that you buy for it is going to, of course, increase its price. So I ended up spending about $3,000 in total, American dollars. Now, Carbide 3D is an American company, and everything is manufactured and built here in the United States. This is a very custom machine. So after doing a lot of research, I thought that this was the best bang for the buck. And I'll talk about a little bit of advantages and disadvantages and do a quick comparison with a few other machines. Now, since I'm a new user, I thought it would be also interesting to go through the procedure of making one PCB and see how it turns out and how it will come out. I've also made some modifications to the machine which you might find useful and if you want to do the same thing to your machine. So let's go ahead, take a look at some of the specifications, just a quick overview, and then we'll take a look at the machine in details and see what we can make with it. Well, let's take a look at this unit. Now, as you can see, it's a fully enclosed instrument here. And this enclosure is pretty important because it keeps the dust out, gives you some sound protection, but most importantly, it keeps you safe because those bits are very hard material and very brittle. And when they break, and they will break when you're doing something, if you do something wrong, they will fly out of the machine and it can be quite dangerous. So you should always run it when it's closed, and you should always be wearing goggles, as you can see with the warnings here. And you should never stick your hand in it when it's doing something because you can get pinched. These are very strong motors. Remember, you can machine aluminum with this, so they will be quite dangerous. Now let's take a look inside. Now, one of the main reasons why I bought this unit as opposed to some of the competitors is that this is a full aluminum chassis machine. So even though you see these PTFE sides and you can choose which color you want when you buy this unit, these are essentially just for the enclosure. The structural integrity of the machine is completely based on an aluminum chassis, which is custom made. So even if you remove this, the machine will be just fine. And I really like that. As you can imagine, you do want something that's very solid, and this definitely provides that. Now, the spindle in the middle is also a completely custom design. It's a somewhat of an unusual design. And if you look closely, you can see there is a belt-driven system. So we have a brushless motor with a belt connected to the spindle. Now, after the belt ratio and everything, the maximum RPM we can get over here is 10,000 RPM. And this is really one of the main limitations of this unit. I would have loved to see this to be able to do 20,000 or 25,000 RPM, especially for doing PCB and precise work. This would be quite handy. Now, at 10,000, I guess it's fine for the applications that I want, but I would have loved to see 25,000, especially because some of the other competitors do go to higher RPM. Of course, they do cost more as well. This heatsink that you see here is something that I installed here. Over long work, this thing can get a little bit warm. It's not really necessary. It's just to make it a little bit run a little bit colder and take the edge off. And if you look carefully, you will notice that the main spindle, as well as the bottom, which you cannot see right now through the camera angle, these are all riding on 20 millimeter bearings. So there are no belts that drive anything in this. Everything is riding on bearings, which is fantastic, gives you very high precision. The slope of the screw here used to move the X, Y, and Z is chosen as a compromise between speed and accuracy. So you can have fast movement as well as very precise movements, and we'll take a look at the specification in just a second. Cable management is great. I really like that. You can see there's absolutely nothing that can get in the way. All the cable is contained within this unit over here, and as the head moves, it will just unwind and wind back, and everything is very nicely done. I don't see anything sticking out that could potentially get caught, or during aging, it can get in the way. So I'm very happy with the custom design of this. Now let's take a look at a couple of other things here. Now here you can see obviously the table will move back and forth there, and I will talk about what this piece is. This is a custom piece that I've made for the machine for some specific reasons, and we'll go over that when we're doing our experiment. And if you look over here, there is a tool depth measurement here that will be automatically built into the machine. This is a huge help. If you've ever used any of these, you will know immediately why. So every time you change the tool, because you don't exactly know where you put the tool in, how much you've inserted the tool into the spindle, this will remeasure and give you exactly the same reference point each time. Very handy, so that especially because this is done automatically. When the machine tells you that there's time to do a tool change, it will automatically do that for you. So everything else other than that looks very nice. We've got power here, which is right now turned on, and the only two interfaces to the machine is a power supply and USB, and that's it. And the power supply is quite large, as you can imagine. because it needs to run all the motors and the spindle and all the electronics. You cannot see any of the electronics. It's all embedded at the back of the unit there. Very nice, very happy. It's quite a good looking machine actually. So let's go ahead and take a look at some of the specifications, do a quick comparison on the computer, and then let's see what the software does. And here's the specification for the Nomad 883 Pro. And as you can see, the travel in the X and Y directions are 8 inches each. This gives you roughly the largest PCB area that you would be able to work in, or any other material that you would want to put through the CNC machine. The travel in the Z direction is 3 inches. Now that doesn't matter if you just want to do PCBs, but it will become important if you want to work on any other material. The speed in the X and Y, Z directions are fairly typical. The mechanical resolution and repeatability are quite good. 1.5 mil for repeatability is respectable. And the mechanical accuracy of 5 mil per foot is also fairly respectable. Now the spindle speed limited to 10,000 RPM. Yes, I wish this was better than that, especially for PCB work, but here it is and we would see how it performs. Everything else is really pretty straightforward. Now I did consider other machines, specifically Othermill, which was another Kickstarter project, which now I think is called Bantam Tools. They did some rebranding. Now if you look at that, the specification for that machine was better in some areas. For example, the spindle speed goes up to 26,000 RPM, which is significantly better than what I get from the Nomad. The accuracy is comparable, 0.003 inches per 6 inch of linear travel versus 5 mil for foot. So it's about the same. The repeatability is better than what I get on the Nomad. But at the same time, this machine costs a lot more. And one of the main reasons why I didn't go with it, well, obviously one was because it costs so much more. So we're looking at $3,200 for the basic bundle, and the Pro bundle is $4,000, which is really a lot. And the other thing is that I don't believe this particular machine has a full aluminum chassis. I think it still has non-metallic chassis parts, although it does have obviously metallic bearings and linear bearings and everything. So that from that point of view, obviously is very good. Otherwise, you wouldn't be able to get the kind of repeatability and resolution that it does. Now, this is also much smaller, much lighter, definitely intended for PCB work, and I'm sure it works really well. I just couldn't justify the price, and I felt that the Nomad is a much better purchase in terms of bang for buck. So that was really my reason for going with it. Also, if you want to work with some other materials, I think the working area and the rigidity of Nomad will certainly help. Other than that, I think it's pretty straightforward. Now, the software that comes with Othermill is, I think, also a little bit better, but the software that comes from Carbide 3D for the Nomad, it works quite well. Let's take a look at that. There are 3 pieces of software that you get with this machine. The first one is Carbide Motion. This software controls the machine completely. It's connected to it through a USB port, and then this is how you can upload a file into the machine for CNCing. Now, one of the very first things I did is that I upgraded the firmware of the machine to version 1.1. This is a beta experimental firmware, but it allows you to use Carbide Motion version 4, and it gives you some really good additional features that Carbide Motion version 3 did not. For example, you can do live speed control as the code is being uploaded to the unit, which is quite handy, and we'll take a look at that. The second piece of software is Carbide Create. This is a 2D, 2.5D software, and it can interpret DXF and other CAD tool files so that you can create a toolpath and ultimately use Carbide Motion to send it to the unit. The other one is Meshcam. Now, Meshcam, you get a license for it. Here I have Meshcam version 7, and it specifically has all the features and characteristics of the Nomad built into it, so you can create a toolpath and all the milling parameters for the machine specifically. This can be very handy. Here I just simply loaded an image, and it will interpret the image as a 3D, and it can do all kind of fancy work on it. Really nice, not PCB related, but nonetheless it can be quite handy. Now, there's another beta software that Carbide has released, and it's called Carbide Copper, and this one runs in your browser. This will allow you to put some Gerber file into it, and then it will create for you all the machine code required to download it into the Nomad. Now, this is in beta and it's very, very limited. And as far as I could tell, you cannot tell it, for example, the depth of drilling and all that. You can just create a toolpath for you, and it has some default value, and I couldn't figure out what that is. Again, this is an experimental software, but we'll use it anyway, because as a brand new user for CNC machines, I just wanted to know how easy it is to go through the entire process. So what should we try as our first board? Well, I could design a board and could make a schematic and do everything. I'm going to save that for a different video. I have some microwave designs that I want to share with you guys, which should be pretty fun. But right now I just want to see the flow. I want to see what kind of board I can produce. So I went ahead and I made in Eagle, a very simple board, and this is it. It's a tiny one. It's 29.5 by 40.6 millimeter, and it has some features on it, as you can see, some drawings of shapes, just to see what comes out. So let's go ahead and open this and take a look and see what kind of dimensions we're dealing with here. So I have set my grid to 0.25 millimeter. Now that's equivalent to about 10 mils, just under 10 mils. So some of my structures are tiny. For example, this one here is just a 10 mil by 10 mil square and spaced out by 10 mil to the adjacent one, and it slowly grows to be larger and larger and larger. So we can see what happens to these structures. And I have some lines here. These lines are also 10 mil, just under 10 mil, 0.25 millimeter, and the spacing varies, as you can see. Some circular structures, some thicker lines, some wider circles. These are half a millimeter, these are 1 millimeter. So you can see a few different structures. So we should be able to use this. Now, what can we do with this and how can we get it into the machine? Well, you need a processor, a CAM processor. It turns out that in order to create the proper Gerber files for our machine, Carbide 3D has already created a CAM processor specifically for Eagle. So we can go ahead and open it. Here is Carbide 3D's CAM processor. We open that, it sets everything for us. It's going to create a Gerber RS274X version. Now we only are using top layer, so that's not a problem. So we've already selected the top layer there, and we can go process selection, and it will create our Gerber file. Is it there? We can go in the directory, and yes, indeed, it is there. Here is our top layer Gerber file. So now what do I do with this? Well, I can go back to Carbide Copper, the online site and the online application. Now remember, this is very, very primitive, as I already described, but let's go and see what we can do with it. So this is a bottom side only. Sure, I can also fool it and say that it's a top side. It will just mirror it. It really doesn't matter. So bottom side only. Go next. Here I can load my Gerber file. Here is my Gerber file. Load it, and it should show up here. There it is. Here's everything. Very nice, and you can see it's showing very clearly the isolation passes. So it has 3 isolation passes around it. Now I don't necessarily want 3 isolation passes, so I would say let's just do well, we can do 1 pass. Yeah, let's try 1 pass. What the hell? Let's see what happens. So 1 pass here, just 1 time around, and just want to see what kind of margins we can get around it. Now, what tool are we using? Well, we're going to be using the 502. This tool is also from Carbide 3D. We can purchase that, and it's a 40 degree 0.125 millimeter. Okay, perfect. So we can go next. Now I don't have any drill holes. I don't have anything, none of that stuff. So we can go next. We can ignore that. We can ignore the outline. Forget all that. And there it is. And this is what we're supposed to get from the machine. If I zoom in here, you can see some interesting features, for example, like that. So you can see it has only 1 clearance pass around each layer. So I'm very eager and curious to see how this would turn out. So now I can save it, generate and save to disk. There it is. It just creates this undefined file. So now I'm going to have to copy it into my directory and load it into the software. Okay, we got our code right over here. So we go now to Carbide Motion. We're going to load this new file, and we're going to load the Nomad test. There it is. So there you go. It gives you all the information about the toolpath extensions that show up. Now we're ready to actually zero the machine. So right now, obviously, you can't just run this. You have to make sure that the bit is in the correct location. So enough of the software. Let's go back to the machine. So let's get the machine ready, but let's talk about dust control for a second. So obviously closing the machine will control the dust, that's no problem. But as with any machine, once you start milling anything inside, dust is going to get everywhere inside the machine. It's going to land on the bearing, it's going to land on the gears. You're going to have to constantly clean it. It can go through the gaps and end up on the table. So there is a couple of ways to avoid that. And the clever people on the Carbide 3D's forum have created something like this. So check this out. This little guy, which actually was machined with this machine also, can be attached to the spindle. So once it's attached to the spindle, this part is permanently there, and the spindle will go right through here so that the bit will be essentially touching whatever that you're trying to mill, and this wouldn't be in the way. And then at the bottom piece we have this, which has got brushes on it, and this can be magnetically connected to the other one, like this. There you go. Now they're both attached to each other, and then underneath this area is where you will be doing any work, and then you can have a vacuum connected to here, so it will suck air out as well as all the particles, all the dust that's generated, and when you're done you will just remove this, change your tool, and put this guy back there. So everything the air will flow through here and then out of there, and of course it will carry all the particles with it. This is great when you have something that has various heights, because this will accommodate different heights. It's very good for CNCing things that create a lot of dust, like wood or maybe even metal, that if you have sufficient airflow, you would be able to carry that out. So this is good and nice, but not quite suitable for PCBs or for what I wanted, and it can get kind of in the way. So what I thought to do is something totally different. Now for PCBs, the situation is actually a little bit more complicated, because especially if you're doing things like FR4, now this board is not FR4, it's FR1, but if you're using FR4, that's basically glass. And when you mill that, you can get particles as small as 30 micron. So you'll have to filter those really well with a HEPA filter, otherwise it's going to end up in your lungs, and it's really, really bad for you. So take that very seriously. This is not something to be taken lightly. It's quite dangerous to breathe in dust, to glass particles like that. So I thought, let's do something to avoid that, and I came up with this solution. Now this obviously doesn't ship with the machine. This is something that I specifically made for this machine. So this is an aluminum plate that sits on top of the existing plate that the machine comes with. So it screws into this, and it has to be extremely flat because we're going to be using it for PCB milling. In there are pins to allow you to align your PCB and little clamps to screw onto this surface, and so the PCB is really nicely sitting there and completely flat and cannot be moved. And it can even be flipped once you want to do more than one layer design there. But the advantage is that this is actually submerged in oil. So I have the PCB under a very thin layer of oil there, and the oil is this one right here. And I can just fill this up as much as I want until it's covering the surface of the board. And you can see clearly there's some oil in the surface. Now the advantage of doing this is that when the bit touches the PCB and it starts routing, you won't have dust coming out because it's completely submerged under the oil, and it will contain every debris that will come out from the CNC process. And also, of course, oil will extend the life of your bit, and it will give you nice clean cuts there. But of course, you're going to have to make this, and it's not easy to do that. And I also have two plugs here, which you can even connect a pump and constantly circulate oil if you really wanted to. Right now, they're just closed. And then you can put any pump outside the unit or on the side of the unit here to continuously change the oil and filter it, so that as it ages, you wouldn't have any problem with that. Now, normally, the machine will come with something like this. And this will be screwed onto that original plate underneath here, and then you will tape your PCB with a two-sided tape on top of here, and then you will have to take the tape off. But I didn't want to go with this direction, but this is definitely a possibility. You can also buy a metallic plate here with a lot of screw holes so that you can have a lot of flexibility in attaching different things to the machine, but this is not going to be required for this. So here we are. We're good. We're ready to go. Now we just have to initialize the machine and zero the machine. Now zeroing the machine is also a little bit tricky for PCBs, but we're going to take a look and see how that is done. But first, let's go through the initialization. So after you initialize the machine, which is really straightforward, then you can align and zero the machine. So here we have a very basic set of controls, which allows us to move the machine in all three axes with various increments, the smallest one being 0.01 millimeter. So I can change the increment to 1 millimeter or under fast, which means it will move on very quickly, so you can get to your final position fairly quickly. And then you can reduce the steps so that you can fine tune it. Now, bringing the X and Y to the zero position is easy. Now bringing the Z to the zero position is a little bit more tricky. And I have a little method to do that using a multimeter. Let's take a look. So I've brought the tool very close to the surface of the PCB. It's not quite touching. I'm happy with the X and Y position. I can maybe move it a little bit in each direction. But I would say, yeah, I'm pretty happy with where it is right now. So we can now go ahead and try and zero it. So the question is, how do we detect when the tool touches the PCB? Well, it turns out that there is a difference in resistance that we can easily measure. And the resistance between the tip of this probe to the chassis when it's not connected to the PCB is about 150 ohms, and sometimes it's about 50 ohms. Obviously it has to do with the bearings and the position of everything, because the machine is connected together obviously electrically, but not very well. But as soon as the tip touches the surface of the PCB, we're going to get 0 ohms, roughly 0 ohms. So we can use that to detect when we make that contact. Well, how do we do this? Well, we can connect two alligator clips directly to the tip of that bit there and one of the screws on that are holding the PCB down. So that should be pretty easy. Let's set that up. And here is our setup. As you can see, the resistance between the tip and one of the screws that's holding the PCB is 128 ohms, and I can very, very slowly move the tip down and getting it closer and closer to the PCB until we hit 0 ohms. I think it's almost there. Let's keep going. You can see the resistance changes a little bit each time there's a step. That's because of the positions of the bearings. But we're getting closer and closer to a point where it will be touching the PCB. So I'm going to keep going until I get that resistance down. It's very difficult to see the distance. It's difficult to judge it. There you go. We're still good. We should almost be there any second now. There you go. There it is. 0. So now if I move it up by exactly 10 microns, so we're dealing with 0.01 millimeter. So if I move it down by 0.01 millimeter, we get a short. If I move it up by 0.01 millimeter, we have nothing. So we're at the resolution of the machine here. So it's as precise as I can possibly get it. So now what I do is that I'm going to raise it by 100 micron, 0.1 millimeter. Why that number? Well, in the software that you saw, I actually can't control the depth in which it goes down. And I did some experiments, and I think 0.1 micron should work, or it may be not enough. But anyway, this is an experiment. We'll find out. So right now where it's shorted, I will move it up by exactly 0.1 millimeter, and then we're going to run the code and see what happens. Okay, file is loaded. Let's run this and see what it does. So here we go. Starting. Now, very first thing it's going to do is going to go up and it's going to ask me to install the tool, but I already have the correct tool in there, so I can just say, yep, it's already there. And now it's going to measure the tool to make sure the height of it is properly calculated. And then once that's done, it's going to go right down and start doing the milling. So let's see what happens. That's exciting. Here we go. Zoom in here. It's going to get started. Here's the motor. And here's the first position. There it is. It's doing it. So I'm not sure if the depth is correct, but we're going to find out. Here's the first one. Oh, I don't think I can focus that much. So I don't know how well you can hear me, but the machine is actually surprisingly quiet. So now we're going to let it go through all this and see what happens. And I'll let you know exactly how long it takes. And here we go, we're done. So now we're going to take this out, clean it up, and put it under the microscope and take a look at some of the features. Now looking at it, I can already see that the depth was too much and it basically destroyed some of the traces. But we can still get some information about the quality of the traces, and then we can judge and adjust for our next PCB. Alright, here is the result under the microscope. Now, as you can see right off the bat, we have a flatness problem. So on the very right side of the board, this is where the clamp was, and the board is the lowest. So the drill bit didn't have enough penetration to actually clear the copper completely away. As we move away from the clamp, we can see that the board would rise a little bit, and then we'll have sufficient penetration. Now these lines are our thinnest lines. They're supposed to be 10 mil, just under 10 mil, 250 microns. So let's do some measurement on these lines. Let's take this one over here, for example. So I'm measuring right across it as well as I can do with my mouse here. And we're looking around 250 microns. It's actually quite accurate, but some of them are a bit thinner. Let's take the one at the bottom here. I would say this is probably a good one. There you go, 0.186 millimeters. So yes, it is about 17 microns too short, too narrow. And I think this is because we were etching a little bit too much on this side. And as we get further and further away to our right side, we get wider lines. Now, I'm not sure if this is good enough for normal use. I'm not sure. We have to do some more experiments and build bigger circuits with it. But nonetheless, I'm fairly happy with the result we're getting. Let's measure another one of these guys. And I think this is probably fairly okay. Yeah, they're about 250 micron. Not too bad. Now, the distance between two lines from the center to center is supposed to be 0.5 millimeter. And we are about 0.5 millimeter. That's not too bad. And then further away, we should be about 1 millimeter. I think from here to here is 1 millimeter. There we go. And we get 1 millimeter. So the distances are quite good. That penetration depth is going to be very important, and the calibration for that is going to be very important. So we can also measure one of these squares. This square over here should be 2 millimeters across. And it is 2 millimeters across, no problem. And the smallest square at the right, it's almost disappeared. That's supposed to be 250 micron, but the one right next to it is supposed to be 0.5 millimeter. And you can see that it's also 25 microns or so short. So this is all normal because we are etching away a little bit too much, and as we get further from the clamp, you can see the result gets better. So I'm quite happy with these, and you can see some roughness around the edges, and this is where the speed, the RPM would be really helpful. Unfortunately, we are limited at 10,000, but I think with a better, higher RPM, this might have been better. And also I'm using this particular PCB may not be very good. So I'm going to get some FR4 and we're going to try it on that and see how much better these things can possibly be, or maybe even worse, depending on the material there. So now let's look at some of the other section. So here's the circles. And as you can see, these circles, this outer circle here is also has some etching or some cutting issue. And this is again because we're close to another clamping point, or closer to the clamping on the right side there. Now, if I go ahead and measure the distance from here to here, we also have about 250 micron, which is what it was supposed to be. And these lines over here are supposed to be 0.5 millimeter. And you can see they're cut a little bit too much. The penetration depth here is definitely more on this side, and if I measure another one from here to here, you can see we will have exactly the same issue in terms of cutting. But from center to center, let's try the result of from center to center. From here roughly to about here, we should have about 1 millimeter, and we do. So the distances are definitely not too bad. And the final big circle, you can see again some roughness around these edges here, but everything else looks fairly good. From this thickness here, which is supposed to be around 1 millimeter, you can see it's definitely cut a little bit too much, the penetration depth here. If you were to compare the thickness of this, we can actually measure that, how deep this cut is, right? It's about 250 micron, this cut. Whereas the first one, you can measure this, and the cut here is quite a bit narrower. Yep, you can see it's quite a bit narrower. It's about less than a factor of 2. So definitely there is some flatness issue, and that's going to be very critical. So I'm going to have to think about how to improve that so we can get better results. But this is not too bad for our first experiment. And there you have it, a quick look at the Nomad 883 Pro. As we can see, it's a very capable and precise machine, and I'm eager to do some more work with it to be able to judge its performance across more examples than just some test patterns. Of course, we have to make full PCBs with it, and I'm going to have to do that in the future. And again, it's thanks to my Patreon supporters that I can even afford this machine and have it here in the lab, and this opens up a whole new set of possibilities. We're going to do microwave PC design, we're going to do filters and active devices and lots of different things that we can do, and actually go through the calculation and see the PCBs built and compare versus theory, compare versus simulation. So it's going to be really exciting, opens up a whole new chapter of things that I can do here on the site. So and thanks to my Patreon supporters that we can do this. And if you're not supporting the channel, the link is below. Please do consider it. And if not, that's also fine. Please enjoy the videos. These are for the benefits of everybody. And leave me a comment. Let me know what you think. If you have any suggestion, any ideas, if you have any experience with this, or if you have any comments about another PCB milling machine, especially Othermill, which I briefly showed, let me know what you think about that. And if you have any other ideas about keeping the board flat, let me know. I think it's going to be quite exciting, and I'm looking forward to making more videos with this.